Okay, so we've got one more set of notes to do before I return to class, and then we'll finish the other ones while I'm there. So I now want to take a look at pages 4 and 5. So we're going to continue on with 4. We're going to talk about this stuff on page 5, at the bottom of page 4, and then we're going to go through and do the problems on page 5 as well. So if we're taking a look at the graphs with asymptotes, so there's a whole section at the bottom of the notes on page 4 that I do want you to read. However, there are 2 of them that you and I are really going to focus on this year. And those are, let's see, the first ones we're going to be doing are horizontal asymptotes. So if we had some sort of graph, and the first one that you and I are going to deal with is called a rational function. So it's going to have a horizontal asymptote at some location that'll be determined by the equation. The asymptote is like a boundary line. So the graph is going to get super close to it, but it'll never actually hit it or go across it until you get to pre-calculus next year. So there are some situations where a horizontal asymptote can be crossed. They're very rare though, and again, your pre-calculus teacher will talk about it. This year, we're not going to cross asymptotes at all. So one of the types of equations that you and I are going to focus on later are exponential graphs. So you've got this horizontal asymptote, which actually should look familiar back from integrated 1. That was one of the other big concepts. And then you have this like hugging effect on one side, and then it slowly starts growing away from the asymptote itself. So this is going to be our first focus when it comes to asymptotes, but then as we move on throughout the year, we're going to be talking about graphs with vertical asymptotes. And just as a heads up, they are going to be the inverses, so something from integrated 2, inverses of the exponential graph, so the first one. So what happens is you get this whole like flipping effect. So what was horizontal now becomes vertical. And then a vertical asymptote, guaranteed, doesn't matter what math class you're in, at any level, you will never, ever cross or touch a vertical asymptote. It simply just cannot be done. So even when you get into pre-calculus, calculus, so on and so forth, you will never, ever cross a vertical asymptote. And then your pre-calculus teacher will talk about it more in detail, or your calculus teacher, kind of depends. So on the same idea, but it's still that hugging effect. So the graph gets infinitely close to this boundary, this invisible boundary, which is what our dashed line is, and then it slowly starts growing further and further away. Now, if you take a look at the notes, you'll see that we have slant asymptotes, so asymptotes that run diagonally. You'll deal with those in pre-calculus. We will not deal with those at all this year. And then you can have a vertical and a slant. There's a whole bunch of different combinations that you can have. However, these 2 graphs represent the types of things you and I are going to be dealing with this year, in addition to one more, didn't leave myself some space, that has a vertical and a horizontal asymptote. And that is on the notes. It's actually the first example for the asymptotes. So we will be getting to those though. All right, so now we're up at the very top of page 5. And up at the top of page 5, we have a problem. So we've got a system of equations. It's 2 or more equations. And you decide the method that you would like to use to be able to solve this. So we could do algebraically, where you bring the 2 equations together somehow, or you could try graphically, and then look for points of intersection. Either way is fine with me, however you choose to do it. I'm probably just going to do it algebraically. So if you take a look at these 2 equations, you'll see that both of them are y equals equations. Since they're both y equals, go back to integrated 1, the whole idea of equal values method or substitution, you actually set these 2 equations equal to each other, which I think is what I'm going to do. Now, it doesn't matter which one goes on which side, just make sure that you don't mix them up at this point. So we want one side equal to the other side. Again, since they're both y equals. So if we take a look at this, excuse me, you see that we've got x's in multiple places on the equation. I've got an x on the left-hand side that's trapped inside the parentheses. I also have an x on the right-hand side that just has stuff kind of flying around it. So if I went through and I square rooted both sides, just get rid of the squared, then it's going to clean up the left-hand side nicely, but it's going to turn the right-hand side into a terrific mess. So I think the best thing to do would be to multiply out the left-hand side, so I don't have anybody trapped inside parentheses at all, and then decide where we want to go from there. So remember, x plus 2 quantity squared is x plus 2 times x plus 2. So I would draw the box, or I would go ahead and multiply that out, which gives me x squared plus 4x plus 4. And then bring down the other side. Okay, so now at this point, excuse me, again, one of the things that you guys did back in Integrated 2, you actually solved a lot of these. You'll notice that I've got an x squared, which I cannot eliminate because there's no other x squared on the other side, so it's not like that's going to cancel. And then I have the x's as well, so you can decide whether you're going to factor or you're going to do quadratic formula or you're going to complete in the square, kind of like last class. So I think what I'm going to do is I'm going to move the 2x and the 4 over to the other side, just kind of see where I'm at. If it looks like it's factorable, I'm going to factor it. If it's not, then I have to decide. So nothing happens to the x squared. I'm going to add the 2x to the other side. That gives me a 6x. And then I'm going to add the 4 to the other side, and that gives me an 8. All right, so I'm going to x squared plus 6x plus 8. I think this is factorable. So if I go through and draw out the box, if that's what you need to do. If not, remember, this is just a tool for you. So if it helps, great. If you don't need it, don't do it. It was just to kind of help you along the last couple of years. All right, so I got an 8x squared, and then I got a 6x. I think this is 4x and 2x. Put those into the empty spots, and then factor. Notice there's no negative signs inside, so I don't have to worry about any minuses. Whoa, that's not right. All right, that's better. Okay, so I'm going to go ahead and replace. So I'm going to get x plus 4 and x plus 2, and that's equal to 0. And go through and solve. This gives me x equals negative 4 and x equals negative 2. However, you're not done with the problem. If you take a look back at the original question, you were supposed to find the points of intersection. You need to have an x and a y. So again, as you move on through math, you're going to move into three-dimensional stuff, so you'll have x, y, and z. You just want to make sure that you solve for every single variable that's actually in the problem. So I've got my x's, I just need my y's. So go back to the original equations, the y equals x plus 2 quantity squared, or the y equals negative 2x minus 4. It doesn't matter which one you choose. Assuming that you have the correct answers of negative 4 and negative 2, then you'll get the exact same answers otherwise. So I'm just going to choose the one that I think is easier. And oddly enough, and I think people would probably pick the y equals negative 2x minus 4. I'm going to pick the y equals x plus 2 squared because I don't think there's as much going on. I don't have to multiply by a negative 2 and then subtract the 4. So I think I'm just going to bring up. So I'm going to start over here with the first equation, which was x plus 2 squared. And then plug in. So if x equals negative 4, I'm going to get negative 4 plus 2, which is negative 2. Negative 2 squared is positive 4. All right, so one of the answers, I plugged in a negative 4, and I got a positive 4. I'm going to do the exact same thing with the other one. So y equals x plus 2 squared. Plug in my negative 2. And one of the things that's nice about this, too, is I don't honestly need to see that this is happening. You can, I think, you can take a look at this, do the mental math itself, and then write down the answer. So I know negative 2 plus 2 is 0. 0 squared is 0, so that gives me 0, but all I really care about is the actual solution. So negative 2, 0, negative 4, 4. So if I were to go through and graph these exact same solutions that I would have gotten if I was graphing and looking for points of intersection. The only thing with graphing I'm not necessarily a big fan of is that you have to make sure that you have all of the points where they could hit each other. And then there's always the off chance, which is actually fairly common, that the points of intersection are decimals or fractions. And so good luck finding those on a graph. All right, so let's take a look at the next page. All right, so the next page was about polynomials. So make sure that you read the middle section there about polynomials. Again, something you've been dealing with for years now. You may not have called it polynomials. I think last year we did, but maybe not in Integrated 1. So now we're just looking at the degree and the coefficients. So this isn't bad. The only thing that I would want to change that I don't particularly like about this question is that a polynomial we want it, I would like it to be a polynomial equation, not a polynomial expression. So because normally you're graphing stuff like this or trying to figure out what this information means to you. So I would go ahead and rewrite it as y equals 3x plus 5. So I'm still keeping the 3x plus 5. I'm just going to attach a y to it. It's not necessary. It just makes me feel more comfortable. Okay, if I take a look at this, the degree, well, I want to take a look at the right-hand side itself, only over here. So if there's the y equals, or if there's a y involved, just make sure that everything's on the other side of the equation. I'm going to look for the highest exponent possible if it's all multiplied out. So notice that 3x is independent of the 5 because they're separated by a plus or a minus sign. That's how I know that it's been written out in standard form, which means there's no multiplication still happening. Each term is independent of the other. Now I'm just going to take a look for the highest exponent on the variable itself. Well, I only see this x right here. If there's no exponent on it, then the exponent itself is going to be 1. So the degree represents, in expanded form like this, the highest exponent, which is just going to be 1. Now the coefficients, remember that coefficients are numbers attached to variables through multiplication. So if I take a look at this, there's only one variable here, which is x, and the only thing that's being multiplied to it is 3. So the coefficient is 3. That's it. 5, just to be clear, is a constant. It is not a coefficient. It's not attached to a variable. So it gets a different name or different type of categorization. All right, so let's take a look at the next example, and that's it for that problem. If I take a look at the next example, notice that everything is still multiplied out. So the 7x to the 5th is added to, so it's independent of the 2.5x cubed, which is subtracted, okay, the half x. So they're all independent of each other. So at this point, I would say that the degree, I'm just looking for the highest exponent possible, which is 5. So the degree on this is going to be 5. Now my coefficients, there's 3 x's in here. There's the x to the 5th, the x cubed, and the x. The 7 is a constant, so we're not going to list it. So the coefficients, I'm just going to go ahead and list in the order in which they're attached to a variable. So highest one first. My first coefficient is 7. My second one, x to the 3rd, is the next highest exponent. And then the last one, and it's going to be negative 1/2. Okay. And then the last one here, this one's different. So you'll notice that there is multiplication happening between the terms or between the variables. So it's not everything strung together with addition and subtraction signs. So you can, which I would recommend that you do at this point, get rid of all of the multiplication. So distribute everything out, combine like terms, get it all cleaned up so it looks like the 2 previous examples. So with that said, I'm going to keep the 2 out in front. I don't like distributing my GCF, which is what the 2 is, until the very end so I don't accidentally distribute it too many times. So I'm going to multiply the x plus 2 and the x plus 5. So take out the box if you need to. If not, go ahead and distribute. That gives me x squared plus 7x plus 10. Then distribute the 2. Now it looks the same as all of the other ones, so the previous 2 examples. So my degree, notice that everything is, every term is separate or independent of the other because they're separated by plus or minus signs. I would say that my degree is 2, so it's the highest exponent. My coefficients, you'll notice that I have 2 of them now. Remember, the 20 is a constant, so it doesn't get included. The coefficient that is on the highest variable exponent is 2. Then the next one down would be 14. So those are going to be my coefficients themselves. And I think that brings us to the end of the notes that I wanted to do today. So next class period, I will be back. Thank goodness. And then hopefully we'll be able to get the notes done. It'll be pretty close to the end of the chapter, and then we'll have the group quiz coming up. So make sure that you keep an eye on the dates and everything that we're going to be doing. I will be back on August 24th. I'll see you soon.